Okay, in that case, we can start. So far in the course, we haven't been worried about the uncertainty coming out of neural networks, or if there are any ways to do uncertainty quantification. I think it's a good time to do it because then you're going to be able to see it visually speaking and then appreciate it more, why you care about uncertainties. Let's say you have some input image, you have a semantic segmentation algorithm like DeepLab, and it's giving you this prediction. And then your self-driving car, you're sitting in a car, is seeing that image as an input, and it's interpreting the image this way, and it's driving based on that interpretation. Now it's a matter of, do you really trust the predictions that are coming out of this segmentation? Let's say you want to turn left. Is it correctly classifying these pixels as curb and the road and deciding properly, or is it gonna hit this post while driving? How uncertain is your model? And if it is uncertain about its prediction, it should tell you, I'm not sure what to do here. Help me, please. Maybe take control, maybe pull over. So the uncertainty matters a lot. Now you have two sorts of uncertainties. One is aleatoric uncertainty. The other one is epistemic uncertainty. Epistemic is the uncertainty of your model, which can be explained away. Given enough data, your model is going to get more and more sure about its predictions. The other one, aleatoric, you're not going to be able to resolve it anyways. It's because of the noise in the data. Regardless of how much data you put, you're still going to have these sorts of uncertainty. So this is noise inherent in the observations, the noise that you're seeing here. And then you can have two sorts of noises. For instance, you can have a constant noise for every image and every pixel in your images, or you can have per image, per pixel noise. This is called heteroscedastic. The other one is homoscedastic. And this is a modeling assumption that you're going to make. This is going to help you write down the likelihood of your data. The other one is the uncertainty of the model. Maybe because it hasn't seen enough data that resemble this prediction, it is pretty uncertain where the curve is, where the road is. And it's a suggestion that you need to show the model more data. You need to train it with more data. And then you can explain away this uncertainty. Let's start with epistemic uncertainty, the uncertainty of the model. And to be able to talk about uncertainty, you need to go and work with some Bayesian framework. And what do I mean? So far, we were saying that our parameters, we're just going to optimize over them. Here, we're going to say that I'm going to put a prior distribution over my parameters. You're going to make some assumptions about the parameters of your model. And then that's going to give you a Bayesian neural network. Why? Because now your parameters have a distribution on them. Previously, they were just parameters, and you were optimizing over them. Now they have a distribution. It means that you have a family of functions coming out of your neural network now. If you keep sampling from your prior, you're going to end up with a new neural network. Then you're going to write down your likelihood, which you are trying to maximize. And this is the likelihood of your model. Given the input to the model, given the parameters, do some predictions. And it could be per pixel prediction. And then you have a data set. Now you want to condition on the data to give you the posterior on the parameters, to update your belief about your parameters, because initially this is very wrong. These are your assumptions, and they could be totally wrong. Now you're going to condition on the data. That's going to give you a posterior, and then you're going to be able to work with it. So that's nice. You can actually condition on the data that you have, and then write a distribution on the parameters. Now you're updating your belief about the model, given the data. Now you're going to write down your Bayes rule. You say P of W condition on X and Y is P of Y condition on X and W times P of W divided by the distribution. And you're always conditioning on X. So you're not marginalizing X out. Okay? So this is always conditioned on X. So far, so good. But what is the catch here? Your neural network is a nonlinear function, and it depends in a highly nonlinear fashion on the weights of your neural network. It means that it's not easy to compute this probability, your marginal probability. You cannot evaluate it analytically. These are not linear models. These are nonlinear models. So this term here is not computable. And because this is not computable, your posterior is not computable. So theoretically, everything was nice and beautiful. But when you actually want to apply it in practice, you're going to face some problems. You cannot compute this integral. There's going to be an integral in P of y given x, where you're integrating out the prior distribution. Okay, what's the solution? Whenever you cannot evaluate something analytically, you're going to have an approximation for it. So you're going to approximate this P of w given x and y with a distribution, and you parameterize it somehow. So this Q of theta star is an approximation to your posterior. Now, by adjusting theta, you're going to be able to get closer and closer to your posterior distribution, depending on the capacity of the family of distribution that you're assuming here. Maybe you're assuming normals, or maybe you're assuming independence per each weight. So you're lowering the capacity. The more assumptions you make on this, the harder it's going to be to approximate your posterior. But what are you going to do? From this point on, you're going to look at the likelihood, because in the end, you want to do maximum likelihood estimation, but then you want to marginalize these W's out. You want to know your marginal likelihood when you marginalize your parameters out, when you integrate them out according to this distribution, which is approximating your posterior. And then you're going to have a likelihood that you can maximize and do maximum likelihood. And you're going to do that with respect to the parameters theta here. Okay? You're going to write down your likelihood. You're going to expand it, take a log from your likelihood, multiply it by a negative sign, because in machine learning, you like to minimize. And then you're going to be able to write an upper bound for your negative of the log of your marginal likelihood. And your upper bound is going to look like this. So this is not rocket science. These are just you writing out your likelihood and then using Jensen's inequality to come up with an upper bound on the negative of the log of your marginal likelihood. So this is the upper bound. This is a number that is bigger than your negative of the log of your likelihood. If you minimize a bigger number, you are pushing the smaller number also down. So if you minimize this, you're actually minimizing the negative of the log of your likelihood, and equivalently, you're maximizing your likelihood. Okay, so far so good. But this term is familiar. This is coming out of a few lines of math, but this term is really familiar. What are you actually doing? This is actually the likelihood of your model for a sample from your distribution, from some distribution, from distribution Q. And then this looks like the weight decay or L2 penalty on the parameters. You want your parameters to be small. So you're regularizing your model. So it's beautiful. What is this WI hat? Where are you sampling from? This could actually end up being your dropout distribution. We were doing dropout already during training, and each example that was going in our neural network, we will drop out some of the weights. That's going to give you a distribution on your weights. And you can actually write down the mathematical formula of that distribution. We don't have time to go through it, but you can actually write it down, what type of a distribution you're going to end up with. It's going to be a Gaussian mixture or a mixture of Gaussians. Okay, so let's analyze this first term first, and then we're going to look at the other term. For this term, an image is going to go in. You sample your dropout. It means that you're going to drop some of the weights, and then that's going to give you the corresponding prediction of your model. And this we were already doing to do the training. Now, when it comes to inference, you just don't take the average of your model. You're going to report not only the average, but also the variance that's going to come out. So during inference, an image goes in, you can sample multiple dropouts or drop your weights accordingly. Now your neural network has multiple predictions for a single image. You can average them out, report the average prediction, and you can also report the variance. And this is actually what you're plotting here. So that's this term. What is the other term? You have the dropout probability showing up here. So it's a little bit misuse of notation. This P is not the same as this P, but that's your dropout probability, which is helping you to regularize your neural network. And you might ask, where is this term coming from? This is coming from you trying to match this approximation or this approximate distribution to your posterior. This is coming out of the KL divergence or an upper bound on them. This is actually the KL divergence between this distribution and your prior, and that's going to give you an upper bound in addition to some other terms on the KL divergence between your Q and your posterior. So that's where this term is coming from. And it's trying to regularize your model. Okay, so far so good. Any questions about this? So I'm omitting a little bit of math here, which is not that crucial, and you're going to be able to, if you sit down and write it carefully, you're going to be able to figure out the details. So it's not complicated. The message that I want you to take home is that this loss that you see here is an upper bound on your negative of the log of the marginal likelihood. And where is the marginal coming in? You're marginalizing out these W's according to your posterior. Rather than doing that, you can marginalize them according to your approximation to the posterior. And then the dropout that we're already doing is giving us this approximate distribution that we are looking for. Okay, any questions? So this is for training. What do you do when it comes to inference? An image goes in, corresponding to that image, you're gonna sample multiple weights according to your dropout. So you're gonna keep dropping out weights. And then in the end, for each image, you have multiple predictions. So you're pushing the same image through multiple neural networks. So you have multiple predictions. You can report the average, which is gonna give you your segmentation. And you can report the variance, which is gonna give you the epistemic uncertainty. And this uncertainty, given enough data, is going to go away. It doesn't mean that it's not crucial. It means that you need to collect more data to be able to predict better, to have a better model. Let's go to the other type of uncertainty, aleatoric. It's easier for regression. It's not this task. This task is a classification, per pixel classification. But for regression, usually your likelihood is coming out of a normal distribution. So this P of yi given the condition on the prediction of the model, that one is a Gaussian distribution. You have exponential of negative of yi minus the prediction squared divided by the variance. And then there are some constants in front of the exponential. The log is going to get rid of the exponential. The negative of the log is going to get rid of this negative in the exponential. And then basically you're doing mean squared error. So this is your square of the errors. At the same time, some uncertainty term is going to come out, plus some constants. And when it comes to optimization, the constants don't really matter. The derivative of your objective function, if it's a constant with respect to your parameters, is going to end up being 0. So they don't matter. And then you're going to have a neural network that is not only predicting the mean, but it's also predicting a variance or a covariance matrix. It is easier to do it as a diagonal, because otherwise you're going to end up with a lot of parameters or with a large neural network. So usually this is a diagonal matrix coming out of your neural network. So your neural network not only is predicting the mean, it's predicting the variance, and then this is going to end up being your predictive variance. You're just expanding your predictions out. So what are you doing here? Your neural network already per each image is outputting multiple predictions. So it's outputting multiple means and multiple variances. You can take the average of those. You can take the second moment of the predictions and then add these terms that are coming out of your neural network. And that's going to give you the predictive variance. And these are just multiple samples from your neural network. And this negative of the log of this probability is exactly what is going up there. Okay? But our task is actually classification. It's per pixel classification. How can you modify that? The prediction of your model goes in. Usually it goes in a softmax, and then you're going to write down your cross-entropy loss. These are the ground truth. These are the predictions of your model. If sigma is 0, there is no uncertainty in your data. And that's just what we have been doing so far. Out of that, you can get epistemic uncertainty of your model. You are not going to be able to get the uncertainty of your data observations, And here you're adding the observations, the uncertainty of your observations. This is how you're modeling it. You keep sampling from normal distribution. You have some variance that is coming out of your neural network. And then you squash both of them through a softmax to turn them into probabilities. So you're adding some noise to the predictions of your model. What can you do? You can do that multiple times, compute the average when it comes to prediction. This is for training. This is for prediction of your model. You keep sampling from normal distribution, put the samples here. Sigma hat and y hat are the predictions of your model. Push them through a softmax, average them out, and that's going to give you a probability, which you're actually plotting here. This is your semantic segmentation. If you look at the entropy of your P, that's going to give you the uncertainty that you can plot here. What is nice about this, each data point, each image, and each pixel in that image are going to have their own prediction. You're going to know the corresponding semantic map, and they're going to have their corresponding uncertainties. One of them is the model uncertainty. The other one is the uncertainty in the data. And that's how you modeled it, the uncertainty in your data. So the likelihood that you're writing, the model likelihood, is also an assumption that you make. And you're making an assumption that your uncertainty is like this. Okay? And then the entropy is going to give you the uncertainty. Was everything clear? Are there any questions?
So in the last two categories, regression and classification, that's a different way to construct the loss function. Is that right?
Exactly, yes.
Okay.
So for regression, your loss function is usually in the form of mean squared error. And for classification, there is going to be cross entropy and softmax.
Okay, I think that's clear. Thanks.
So yeah, so you need to separate these two topics. One of them is training, and this is how you're going to train. The only thing that's going to change is this log of the probability. For regression, it is that. For classification, is the cross entropy. Once the training is done, now you want your model to not only give you the predictions, the average predictions, but also the uncertainty. And you can do that in two ways. You can keep sampling your weights according to your dropouts, and per each example, get multiple predictions and average them out. That's this prediction. And then the variance is going to give you the epistemic uncertainty. The other one is you're actually marginalizing this distribution out. And how do you do that? You do Monte Carlo sampling from that distribution. You keep sampling from your normal distribution. So you can keep sampling from two things. One is your dropout. You keep dropping out your weights when it comes to inference. And then you keep sampling noise. And then you can actually separate them out. Some of them are epistemic, some of them are aleatoric uncertainty. Okay, I guess we can move on.